Okay, so 1.6 is probably going to be the most important thing we talk about so far. There is going to be trig stuff in every single chapter, almost every single section for the rest of the year. This one section reviews every trig chapter from last year. So I want to really make sure we hit this hard. Arc length is not a huge idea. The arc length formula is S equals R theta. The biggest thing that I can say about trig and calculus, everything's in radians. So you're going to have to get more comfortable with radians if you're not already. So as long as the angle's in radians, we just use this nice, easy formula. So find the length of an arc subtended by radius 3. So what that means is we have a radius 3 and an angle of 2 pi over 3. The arc length is just the part of the arc that's intersected by these two radii. Okay? So we find the arc length by taking the radius times the angle, 2 pi over 3, and that's 6 pi over 3, which is 2 pi. So if it's not in radians, the first thing you're going to have to do is change it into radians. Remember, if you're changing something into radians, you just multiply by pi over 180, and that converts it into radians. Okay, so the big thing is sine is always the y value. And if you think of it this way, so if you have an angle, like right here, and I connect this, making my triangle, if this is always the angle I'm talking about, the opposite, so TOA, we will hardly ever use this. We'll always think of things in terms of x, y, and r. My opposite is really my y value. My adjacent is really my x value. And my hypotenuse is always the radius in the unit circle. So you want to think of sine is the y value over r, because that's really the opposite over the hypotenuse. Your cosecant, the reciprocal of sine, so r over y. Cosine is the x over r. Secant is the reciprocal of cosine, so you just reciprocal. Tangent is y over x. Cotangent is the reciprocal. This is what you need to know inside, outside, upside down, right there. And then what we're going to do with it is use our special triangles to solve stuff. So remember, in a 30, 60, 90, the smallest angle always gets the smallest side. So I'm going to make across from 31. The hypotenuse is always 2, and the 60 is always 3, square root of 3. A 30, 60, 90 always has this basic relationship. And in a 45, 45, when your base angles are congruent, the sides across are congruent. We could do our a squared plus b squared equals c squared, but it's our 1, 1, square root of 2 triangle. All right. Okay. So sine inverse of square root of 2 over 2. So first of all, it's positive, so I'm going to place this. I'm just going to create a triangle in the first quadrant. The other thing I want you to think of, this has been fixed because anytime the square root on the top matches the whole number on the bottom, it's been fixed. Oops. This was really 1 over the square root of 2. Remember, you fix it by taking the square root of 2 over the square root of 2. So you have to recognize to unfix this to make this an easy problem. Okay, So sine is y over r. So once you unfix the radical, the y value is 1, and the r is the square root of 2. This is a 1, 1, square root of 2 triangle. So what, and remember, the angle that we're always looking for is the one connected to the origin. So my angle, and I'm always going to name my angle theta if I don't have anything else, is 45 degrees. Because that's our 45, 45, 90. Now, you have to also recognize what is that in radians. Pi over 4 is our 45 degrees. I'm just going to tell you right now, 45 is pi over 4, 30 pi over 6, and 60 pi over 3. Now, you should know this, and I'm just giving you a whole bunch of stuff, so kind of take it. We always start at 0. This is pi over 2. This is pi, 3 pi over 2, and 2 pi. Pi is in the same place as 180. These are equivalent. This is just degree measure. This is radian measure. Pi is equivalent to 180 degrees. So if pi is 180, 180 divided by 4 is 45. 180 divided by 6 is 30. 180 divided by 3 is 60. So whatever you need to do to kind of put that together, this is your basic information here. All right, tangent. When tangent is negative, we always put that into the fourth quadrant. That's our restricted domain that we have to use. If you don't remember your restrictions, if they are positive, they always go in the first. So sine, cosine, tangent. If this value is positive, you put it in the first. The only negative you put in the second is cosine, and the other negatives go in the fourth. Tangent and sine go over here. So because tangent is negative, I automatically put it in the fourth. This is negative square root of 3 over 1. Tangent is y over x. So my x is 1. My y is negative square root of 3. This is our 1, 2, square root of 3. What angle is across from the square root of 3? 60. Now, it's very important though, you're going backwards 60. So this is negative 60, or in terms of radians, it's negative pi over 3. You really need to be fluent in both degrees and radians, but we're almost going to be using radians exclusively. Now, with 0, 1, or negative 1, it's actually easier to use the curve. So my restriction for cosine looks like this. So when is cosine 0 at? Okay, so cosine is 0 at pi over 2. So think of it, this is 0, 1. This is pi over 2, 0. And this is pi negative 1. We'll go over this a little bit more in a second. But the inverse means you're looking at what y value is 0, and the answer is the x. So be really careful about that. All right, here's where we're going to do all the curves, and I'm going to highlight a lot of stuff. So please be careful. First of all, when we graph sine, we did this earlier. Sine is pi over 2, pi, 3 pi over 2, 2 pi. We go to 1 and down to negative 1. Sine starts at 0, goes up 0, down, 0. And it really, I'm going to come back here for a reason. It just keeps repeating that curve over and over and over. I'm going to go all the way to the left, all the way to the right. So my domain is negative infinity to infinity, but my range all fits between -1 and +1. I never go below -1. I never go above +1. How long does it take for this curve to repeat from 0? I start at 0. When does it start to repeat itself? At 2 pi. So the period is 2 pi. Now, we're going to talk about restricted domains later, but you might want to take a highlighter and highlight, that's my restricted domain. All right, so whenever we're dealing just in general, if they don't give us a interval, we're probably just talking about -pi/2 to pi/2 for my restricted domain. All right, so I put cosecant with sine. Now look at, on your note sheet though, it's underneath it. And this is why. Let me actually show you this. If this is sine, what do we do with reciprocals? If sine is y/r, cosecant, we just flip it, right? r/y. So I want you to think about, what are these three values here? Those are 0. Well, what's the reciprocal of 0? 1/0, which we can't do. So every place that sine is 0, its reciprocal, cosecant, has an asymptote. Because 0 does not have a reciprocal, so that's why we put asymptotes. Now, think of it this way. When we're back in person, I'm going to show you something. This little hump here, you just flip it up. It goes like that. This little hump up gets flipped upside down. So this point here is still pi/2, 1, because what's the reciprocal of 1/1? It's still 1. So secant, or sine and cosecant all have a value of 1 at pi/2. Okay? All right, cosine and secant. I'm going to come back for cosine also. 1, 2, 3, 4, -1, 1. Cosine starts at 1, goes down. Be really careful when you draw the cosine curve, because you want to make sure here you come back down. Okay? All right. So think about what I just said earlier. Each place that a function has a 0, its reciprocal has asymptotes. Because cosine is 0 at -pi/2, secant, its reciprocal, has an asymptote. Where cosine has a 0 at pi/2, secant has an asymptote. Three pi/2 asymptote. Then I find my 1's. Cosine is 1 at 0, so it stays 1. -1 at pi stays -1. You just take this upside down u and flip it. Take this up u and flip it upside down. So as long as you know your original sine, cosine, and tangent, you just flip it for the reciprocal. Tangents, almost a little easier. We basically just need to look at -pi/2 to pi/2. That's where tangent has its asymptotes. It kind of just looks like the wiggle, where it wiggles through 0, 0. One thing I always tell people though, at pi over 4, tangent is 1. At negative pi over 4, tangent is negative 1. You just need to know those 2 points because that's going to help a lot when we move forward. Okay, so if tangent is 0 at 0, its reciprocal cotangent has an asymptote at 0. Since tangent has an asymptote at pi over 2, that's where cotangent, its reciprocal, is 0. So I'm just going to kind of flip, kind of continue that pattern on, because think about this would just keep going. At pi is my 0. Now, 1 is still 1. Negative 1, still negative 1. So it's just reflected over tangent. Tangent and cotangent are just reflected vertically. Okay. I think that's all for that. Okay. Period is just how often it repeats. Like if we come back, because tangent and cotangent both repeat after pi, their period is pi. Tangent and cotangent both have a period of pi. Everything else has a period of 2 pi. That's what we call, it's periodic if it starts to repeat. All right, even and odd. So the way I like to think of this, let's think of the cosine curve. Remember how I said even functions are reflected over the y-axis? We actually just, if you flip it, it has y-axis symmetry, and so therefore it's even. Sine is actually flipped over the origin. So when it has symmetry over the origin, it is odd. I think the big thing you just want to remember is that sine is odd, cosine is even. Okay, now finding values is going to be pretty important. It wants us to find all the trig functions of theta. This says sine is negative and tangent is also negative. So let's think about this. I always say to remember where things are positive, all students take Calc. That means sine is positive in the second, tangent's positive in the third, and cosine's positive in the fourth. So this wants to know where sine is negative, which is the third and the fourth, and tangent's also negative, which is going to be the fourth. So I'm going to draw a fourth quadrant angle. Sine is y over r. So that means y is -3, r is 5. When the hypotenuse is 5, this is just our 3, 4, 5 right triangle. So then to draw to find all the other trig functions, I'm still going to write this out, and I'm going to show you why. I always write sine theta, cosine theta, tangent theta, and then underneath I do the reciprocals. Cosecant theta, secant theta, cotangent theta. So if these two are reciprocals, that means their answers are reciprocals. Cosine is x over r. Its reciprocal right underneath is 5 over 4. Tangent, y over x. Cotangent, flip it, x over y. So if you set all 6 up, sine, cosine, tangent, and put the reciprocals underneath, cosecant, secant, cotangent, just find the 3 basic ones and flip it for the reciprocals. So this is probably the most annoying one. We've got our vertical stretch. Anytime you multiply by a number, that's the vertical. The horizontal, this is stretching our period. The vertical shift is easy to find. This is our phase shift. This is probably the best way to write it. This looks so much easier. Now, this value is our amplitude, how much we're stretching it out, up and down. But when we state the amplitude, we always state it as a positive value. Whatever this number is changes the period. Now, what's really important for sine and cosine, you always use 2 pi divided by that number. If it's tangent, you do 1 pi because that's the period for tangent. C is the horizontal shift or phase shift, and D is your vertical shift. So this looks super confusing. Let's see if we can actually demystify this just a little bit. Okay, so first of all, A is 3. Our amplitude is 3. Period. Because it's cosine, we take 2 pi divided by the number next to x. 2 pi divided by x is just pi. Our horizontal shift. Now, the way this is written, I'm going to show you something. I like to factor this number out and divide everything in by 2, because when you do that, this is your phase shift. See, this is with the x, so it moves at the x direction. So I'm going to move the horizontal shift to the right, pi over 2, and that plus 1 on the end is our vertical shift. So we're moving everything up the y-axis by 1. All right, so let's see how this graphs. All right, so we sometimes also call that vertical shift our midline, what everything oscillates around. So the first thing I'm going to do is go up 1, and that's what it's going to shift along. The second thing I'm going to do, A equals 3 means from the midline, I'm going to go up 1, 2, 3, and down 1, 2, 3, and that's how far it stretches. All right, the period to me is one of the harder things. 1, 2, 3, 4. It's always going to look the same because I just make my hash marks match the period. So I'm going to go pi to my last one, cut it in half, pi over 2, cut it in half again, pi over 4. And that's good enough for me. All right, so watch this before you actually start writing this down. So cosine typically starts up. So from the midline, I'm going to be at the top. Then I go down to the midline. Then I go down to the bottom value, back to the midline, back up top. Now, this has everything except my phase shift. So I'm going to make like a dotted line. Because now what I'm going to do is shift each of my points to the right pi over 2. Notice the distance from here to here is pi over 2. So I'm moving this to pi over 2. I'm moving this one over here. I'm moving this one to pi. Moving this one 2 spots to the right. So what did I miss? Oh, this one's here. And you can almost like move it back like that. And that'd be good. Okay. Frequency, the key to this, the reciprocal of period is called frequency. So if you know the period, flip it, that's the frequency. So remember, the number, the coefficient of x is where we find the value to help us find period. This is sine. So period is 2 pi divided by our b value. So our frequency is just the reciprocal. I'm going to tell you right now that you might want to watch this video a couple of times for everything to sink in. There's a lot of information. I will say this example, very little importance, but it's also an easy one. Okay, remember when I was talking about restricting the domain earlier? This is what I was talking about. So I want to come back to our graphs here. And notice from here to here, that is my restricted domain. Restricted domain for sine negative pi over 2 to pi over 2. And the whole reason that we restricted is I want it to be a function. And for the inverses, I want the inverse to be a function. So that means it has to be 1 to 1. Notice that if I do a horizontal line through here, it's not 1 to 1. But if I restrict it from negative pi over 2 to pi over 2, it would be 1 to 1. So the restricted domain is just what helps its inverse have a function. So you might want to go back to this page and for sine, maybe highlight from negative pi over 2 to pi over 2. For cosine, it's actually from 0 to pi, the restricted domain, 0 to pi. And tangent is just negative pi over 2 to pi over 2. Because this gets me the whole function without, and this whole region here is 1 to 1. Okay, so it says show that sine from negative pi over 2 to pi over 2 is 1 to 1 and graph the inverse. I kind of had to squish this in here. So first of all, if I graph sine from negative pi over 2 to pi over 2, it looks like this. Notice this passes both the vertical test and the horizontal test. And so it's both a function and 1 to 1. So here's the key. If we switch x and y for inverses, guess what we're going to do? The x-axis now becomes the y-axis. So on the y, we have negative pi over 2 to pi over 2. Since the y is negative 1 to 1 on the original, the inverse, the x becomes negative 1 to 1. So this point here, negative pi over 2, negative 1, just flips. Negative 1, negative pi over 2. 0, 0, 0, 0. Pi over 2, 1 goes to 1 pi over 2. Now, it's kind of important here. It looks like the 3 points are in the same spot, which is true. But remember, sine is going along the x-axis. The inverse is actually going along the y-axis. So I always say the original sine curve hugs the x, and the inverse hugs the y, kind of curves around it. So this gives us the domain and range for, this is our restricted values. I wouldn't worry about this. If you kind of highlighted your graphs, that's going to be good enough. And this is the actual graphs themselves, which they can be kind of confusing, but they're a good reference. All right, last two examples. So the cosine inverse finds your inverse trig functions. Find angle measurements. Now, this is why. Think of this. Cosine theta equals, and I'm going to say -1/2 because this will make better sense when we solve it. So how would I get theta by itself? I'm looking for what angle do I take cosine of to get -1/2. So if I want to cancel out cosine, I technically take cosine inverse of both sides. So that cancels out cosine. So that's why whenever you have the inverse function, it's finding angles. Now, where is cosine negative at? It's negative in the fourth and in the third. Okay. Now, -1, 2, square root of 3. This is my 1, 2, square root of 3 triangle. So this little reference angle here is 60. This is 120. All right, I'm gonna have to pause this and get back to this in a minute.